Inverse functions. We've already taken a look at the inverse of a quadratic function. Now we will be applying that same idea to any sort of function. Now remember that inverse operations are operations that undo each other. So if I start with any number, let's say the number 22 is my lucky number. If I do an operation such as adding 8, I get some sort of result which is 30. Now if I take that result of 30, if I do the inverse of my operation, I should get what I started with. So the opposite or the inverse of adding 8 would be subtracting 8. So 30 minus 8, you see I get 22, which is exactly what I started with. So adding 8 and subtracting 8 are called inverses because they undo each other and you start or you finish with what you started with. So the definition of an inverse function or inverse functions are two functions that undo each other. So f of x is our regular notation for a function. So we say f inverse of x. So this little, it looks like an exponent of -1. We say f inverse of x if you put in a value of a into the original function, you will get some result b. Just like when I put in 22 into my function, I got the result of 30. If you then take that result and put it into the inverse, you should get the value that you started with. Now remember that the inverse of a function is not necessarily a function itself, so we'll have to check that out. So as an example here, f of x equals 2x plus 1 has this inverse equation. I want to check that with an x value to see if it actually is an inverse. But first, just to review, let's figure out exactly how we got from here to here, how we figured out that inverse. Now remember that f of x is really just your y value of a function. So remember, for figuring out an inverse, you swap the x and y variables. So in the place of y, I'm going to put x. And then instead of 2x, I'll now have 2y. And then plus 1. Okay, so by swapping x and y, I can now use this to figure out my inverse. And what we want to do here is we want to isolate y. Now this is just a linear equation, so it should be pretty straightforward. I can subtract 1 on both sides to get x minus 1 is equal to 2y. And then dividing both sides by 2, I get the equation y equals x minus 1 over 2. So there's my inverse equation. Now the question is this actually a function though? This is what we have to consider. Now right now we're not quite sure what that function is, but just to make it a little bit more clear for you, if I actually divide both of these by 2, what it will become is half x minus a half is equal to y. So it's okay if you get an answer like this, you can divide both of them by 2. So now this looks like a linear function with a slope of a half and a y-intercept of negative a half. Now anytime that a linear function is not a vertical line, so a vertical line has an undefined slope. So this right here is not a function. Obviously one x value would have several y values, but a slope of a half would be a diagonal line. So maybe looking a little bit like this. Okay, so this is going to be a function because each x value will only result in one y value. So that's why we're able to call this f inverse of x is equal to half x minus a half, or x minus 1 over 2. Alright, so I would like to check with any x value to see if this is actually a function. So I'm going to use my lucky number of 22 again. So I'm going to evaluate f of 22 using the original equation, the original function. So 2 times 22 plus 1 will give me 45. Alright, so now what we're saying is, if this is in fact an inverse, if I take that result of 45, so f inverse of 45, and plug it into the inverse function, let's see what happens. So 45 minus 1 is 44, divided by 2 is 22. So you'll see that starting in the original function, plugging in one value, you get a result. Putting that result into the inverse, you get what you started with. So this is in fact a function and an inverse function because of that property there.